Swayam Prabha. Digital India. Educated India.
Okay, good morning. Morning. Okay, so we start off with one more point to be added in the case of instruction set design. This concept is called expanding opcodes. Suppose I need I have operands which can be addressed using 4 bits, and I have instructions which can be 16 bits in length. Okay. So how many 3 address, 2 address, 1 address, meaning 3 address means 3 operands, 2 operands, 1 operand, and 0 addresses and 0 operands. How many instructions can you design? So I have how many instructions you can have, right? Maximize on this. Suppose I have 16-bit instruction length, and each operand will take 4 bits. Let us say I have 16 general purpose register, each operand will take 4 bits to address it. Now how many 3 address, 2 address, 1 address and 0 address instructions you can construct? Is there a systematic way of doing it? Do you understand the question? Yes or no? What?
So,
Yeah.
so only in case of 3 address will use all the 4 bits. Like 16, it's a 16-bit instruction.
But the instructions are constant length, no, I can't adjust it. Every instruction is 16 bits in length.
So I'm not sure, but I think if it's just 1 address case, then we can specify more than 1 instruction in 16 bits.
But I need in this priority, I need more 3 address, less 2 address, 1 address.
Sir, will it not depend on size of the opcode?
So total instruction size is 16 bits, and I need 3 address, 2 address, 1 address and 0 address. Opcode can be whatever, right? Opcode doesn't need any. It can, if you have k bits, I could have 2 power k opcodes. Right. I need a variety of all these things, but I would like to maximize 3 address, 2 address. So what is a systematic way of doing it very quickly, and why should we do it? Yes. At the end, the decoding should also be very simple. As I told you, there are 2 translations involved, right? Compiler translates to machine language. That's an explicit translation which you see with your eyes. The machine language is again interpreted by the hardware. So that's the second interpretation. You are getting this? So you should get me a way by which I can design so that my decoding also becomes simple. First to 4 bit we can use for opcode, yeah, that's obvious. Then
if there is 3 operands, we use the next all the remaining 12 bits, we can use it 4 for each, we can use it for
3 operand, okay. Then
for 2 operand, we leave 0, 0, 0.
how will the hardware know it is 2 operand or 3 operand?
Might need 2 bits for that.
Huh?
We might need to give 2 bits for that, whether it's 3 operand, 2 operand or single operand.
So we will keep 2 bits for that. Where?
We can use 0, 0, 0, 0 to mention that there is no operand there.
But like one German general register right now.
So if you put 2 operands here, that means, see, these are actually needed for 3 operand instruction, these are all needed. If I just put 2 operands here, then what will happen? Only I will have 2 more operands left.
No sir, you can reuse that remaining space if that
Remaining is only 2 bits.
No sir, if you have 2 operand instructions, 2 operand instruction, you can use only like 8 bits The other 4 bits actually were used for an address in a 3 operand can be used for as opcodes in 2 operands.
Okay. So how many? So then tell me. You are getting some idea. Okay. Now can you tell me how many 3 address operand, 2 address operand instructions? How many of each kind can I have? So the moment I say 2 operands are used to specify the number of operands, 2 bits are used to specify the number of operands, I could have maximum 4 here, right? Right? Huh? No, if I want 3 address operand instructions with 3 address operands, then 12 bits are used for that addressing. Remaining you have 4 bits, in which you say that 2 bits will always be used to indicate how many operands are there, 0, 1, 2. So I will have remaining 2 more operands. By that I could have 4 instructions.
If the opcode is 0, 0, 0, 4 zeros, if the opcode is 4 zeros, then it's 0.
So essentially this is what he says is not that optimal. It's correct, but that's not optimal. Okay, now can you start your solution?
If you are using 3, then we will take only 12 opcodes.
12 opcodes,
That
12
is
bits.
12 different operations.
So if I have 3, okay,
4 bits will be left.
yeah, there will be 4 bits left here. Yes.
If the first 4 bits, the value is 0, then we can assume it to be 0 address. If it is 1, it will be 1 address. If it is 2, it will be 2 address. Otherwise, it will represent opcode.
Okay. So you mean to say I'll have 13 instructions.
For 13 different operations.
So you now give me some 13 for this.
Similarly, if it is 0 or 1 or 2, then we can use some next 4 bits for the opcode, and other 2 will be operands.
So how do you go about doing it? How will you form a decoder for this?
First, we can evaluate that value of first 4 bits.
So I have to find out whether it is 0, 1 or 2, right? And still you get only 13. Correct? Okay. Now let me give you a solution. Okay. So if the first 4 bits, okay, first, that is most significant. So this is the most significant bit, this is the least significant bit, left to right. First 4 MSBs non-zero, right. The first 4 MSBs are non-zero. If you take the value of the first 4 MSBs, then it is a 3 address operand, 3 address instruction. So I will have everything. So here all things are possible from 0, 0, 0, 0, 0, 0, 1 to 1, 1, 1, 1. If any of these combinations are there, then it is a 3 address operand. If I have all zeros, then it is not a 3 address operand. Okay. So by this I will have 15 such opcodes. Okay. Now if this is 0, 0, 0, 0, then I will go to the next OP1. This is not a 3 address code, so it could be a 2 address code or anything. If this is 0, 0, 0, 0, if this is not 0, 0, 0, if this is not 0, 0, 0, 0, then it is a 2 address opcode. So what is 2 address? First 8 MSBs second 4 MSBs non-zero plus first 4 MSBs 0, and plus means and, okay, and first 4 MSBs 0. This is, so how many I will have here? I will have 15 of them, correct? I will have 15 of this. Now the next one address is third 4 MSBs non-zero and first and second 4 MSBs 0. So I could have 15 of this, okay, and 0 addresses all first, second and third 4 most significant bits are zeros. So everything is 0, then this is 16 0 address instructions. So I could totally have 45 plus 16, 61 instructions. Are you able to follow? Right? So I will check the first 4 MSB. If it is non-zero, then it is going to be so if it is non-zero, it is going to be a 4 address instruction. So how do you find out whether 4 bits are non-zero? What is the easiest way of finding whether 4 bits are non-zero? OR. We will just do an OR of this. This output of this OR will tell me whether it is a 3 address instruction or not. If I take the AND of this, I put the next 4 MSBs here, right, and if I take the AND of it, it is going to tell me what? It is going to tell me whether it is a 3 address instruction or not. So this will tell me, sorry, 2 address instruction. This will tell me 3 address, this will tell me 2 address. If I take the next 4 bits, okay, and do it here, this will give me whether it is a 1 address instruction. Okay?
Supposed to be 0, sir. Then we have to get not and then AND.
What is it?
For 2 operand cases, the first 4 should be 0.
No, it is not, it is.
We have to use a not and then AND.
Why?
First 4 should be 0, sir. AND will always report 0 then.
Yeah, if it is 0, that's what. If it is,
We need 0 there and 1.
no, if it is 0, then it is not a 3. I am saying it is not a 3. It is. Oh, you are saying, okay. So if it is 1, it is going to be 3 address. If it is 0, it is not 3 address. Okay. So by this I can find out whether 3 address or not. Now if this is 1, it is going to be 2 address. No, I need to put a not and say, yeah, some circuitry here. I will leave it to your judgment. But essentially it will be that whole decoding will be subject to some 2 to 3 levels of gate max. It can be done much faster. So this is one very interesting thing that we need to keep up when we are trying to encode the instruction. One of the important thing in architecture is to find the list of instruction, then how to encode them. So I say add, what is the equivalent zeros and ones for that add? That is what we call as encoding. So the instruction encoding itself should be done very carefully, so that my decoding becomes easy. So there were multiple suggestions that came here, but each of them had their issues. It will not be as simple as what we are trying to do here. At the same time, when I am doing the encoding, I should also keep in mind that I should have enough space for maximum number of instructions. When we design a small processor like this 16-bit instruction, with this I may not have 61 instructions to start with, I may have some 25-30 instructions. But tomorrow when we go and make it into 61 instructions, suppose I do an encoding exclusively for the 25 or 30, then what will happen? Tomorrow I want to add instructions as the architecture grows, then it becomes extremely complex. So when we do the encoding, it should also, because if you take the evolution of all the long standing instruction set architectures, if you look at 8085 versus 8086 to 8386 to the current Intel processor x86 manuals that you go and see, the number of instructions have grown over a period of time. And for me to grow the number of instructions, I basically need a hook to grow it. If I am not going to do something systematic like this, right, then we may land up with a instruction that is instruction set encoding which is extremely complex. So this is one of the very important thing. That is why we just take this concept. This concept is called expanding opcodes. You can just check the web for this. There are many materials on this expanding opcodes. The book that talks about this is Tannenbaum, Structured Computer Organization. The book covers this in some detail, but this is the detail, max detail that you need to get. Okay, are you able to follow? So once you arrive at an instruction set, you say these are all the types of instructions, these are all the actions I want to take, these are all the type of operands, so many general purpose registers are needed, all these suggestions you come. After you come to that, then we need to do what we call as encoding, and when we do this encoding, we need to be sort of systematic so that my decoding becomes easy. Okay, you followed this? Are you able to appreciate this fact? Okay. So with this, I think we have done quite a bit of thing on instruction set architecture. Now we will move on to the next stage, which is pipelining. So now we will go and look at the modern current processors, what we call as superscalar architectures. Okay, so which can do more than one instruction per cycle. It has a lot of concurrency. We will see all those things in great detail in the next 2 to 3 weeks. Okay, right?
I have a doubt, sir. So the click size is limited here, right? But in case of 2 operands, you can actually have more than 16 operands that is used currently.
Yeah, you can, but I have given no, these are the assumptions we have taken. No, first itself I told you operands need only 4 bits per address. I made that assumption.
For 3 address it's completely utilized, but then for 2 address we are not using.
No, if I don't have 16 bits, I can't get 61 instructions of constant length, right? Then your decoding becomes extremely complex. The moment I say I'll have variable size instructions, then your decoding becomes extremely complex. That's the reason. We are driving towards risk. Any other doubts? Okay.